Welcome everyone to today's presentation on respirable crystalline silica dust exposures in agriculture and farming. This work started nearly 10 years ago when we looked at occupational health exposures in agriculture, forestry, and farming industry. Today, we will be discussing about the sources of respirable crystalline silica and some of the research that has been done to date. We hope that you enjoy this presentation. Dust exposures in farming are complex, highly variable, and influenced by weather, soil type, moisture, and mechanization. Unlike construction industry tasks, cutting stone, sandblasting, foundries, farm silica exposures are less predictable and harder to regulate uniformly. In practice, such citations are rare due to difficulty proving overexposure without a specific standard. Also, there is limited OSHA inspection authority on farms. Other agencies, e.g., NIOSH, EPA, USDA, have conducted research on agricultural dust hazards, but there is no binding occupational exposure standard for silica in farming. This transformative remix of scientific work constitutes a fair use of published copyrighted material, as provided by Section 107 of the United States Copyright Law. Some of the content material contained herein including, but not limited to statements or photographs, may contain content not authorized by its owner. All information is to be used for training and educational purposes only. The use of this information is allowed based under fair use and applicable licenses. The University of Texas Health Houston School of Public Health Southwest Center for Occupational and Environmental Health does not endorse any brand name of product, use, or its application as described in this presentation. No financial support was received for the project. According to the 2017 Census of Agriculture, there were 2,042,220 farms and 3,399,834 individual producers, farm operators, excluding hired labor, engaged in the agricultural industry in the United States, U.S. The number of farms has remained relatively unchanged for the past 3 decades, but major changes have occurred in agricultural production, particularly in the livestock sector, which has concentrated into fewer larger units. The number of farms growing field crops has also decreased. The land area used for corn and soybean production has increased, while most other crops have decreased. This presentation focuses on respiratory conditions among self-employed farmers and ranchers who represent most of the agricultural workforce in the U.S. Farmers have a unique work environment and lifestyle compared to the general population. Exposure to grain feed hay dust was associated with the proportion of work time in farming ranching versus other occupation, but not respirable crystalline silica dust. Agricultural dust exposure was recognized in the 16th century as a cause of respiratory disease, and dust exposures continue to be a major source of respiratory morbidity among agricultural workers. Recent research, particularly in the area of dry climate farming, has identified a range of adverse respiratory outcomes due predominantly to inorganic dust exposures. Dust exposures to agricultural workers and farmers are a mixture of both inorganic and organic dust, which may include various other biological and chemical substances. Crystalline silica dust exposures can occur when farm equipment travels on gravel roads, plowing sandy or clay soil, cultivating and harvesting crops, and turning over the unharvested crops back into the soil. Silicates are a predominant inorganic fraction in most soils. They are classified based on the degree of polymerization, which is related to the degree of chemical weathering. Such exposures to crystalline silica is less fibrogenic than freshly fractured quartz, typically found in quarrying and sandblasting. There are only a limited number of studies that focus on the occupational exposure to crystalline silica in the agriculture and farming. Most studies of respiratory disease from dust exposure in the agricultural workplace have focused on allergic diseases caused by inorganic dusts, specifically occupational asthma and hypersensitivity pneumonitis. Exposures to inorganic mineral dusts among farmers and farm workers may be substantial. Such exposures are most frequent in dry climate farming regions. In such locations, farming activities that perturb the soil, e.g., plowing, tilling, commonly result in exposures to farm operators of 15 mg/m, 3 respirable dust, and equals 20 mg/m, 3 total dust. The composition of inorganic dust in agriculture generally reflects the soil composition. Crystalline silica may represent up to 20% of particles, and silicates represent up to 80%. These very high concentrations of inorganic dust are likely to explain some of the increase in chronic bronchitis reported in many studies of farmers. Pulmonary fibrosis, mixed dust pneumoconiosis, has been reported in agricultural workers, and dust samples from the lungs in these cases reflect the composition of agricultural soils, strongly suggesting an etiologic role for inorganic agricultural dusts. However, the prevalence and clinical severity of these cases are unknown, and many exposures are to mixed organic and inorganic dusts. Epidemiologic studies of farmers in diverse geographic settings also have observed an increase in chronic obstructive pulmonary disease, morbidity, and mortality. Today, we will focus on respirable crystalline silica in the soil, but we are aware of many other occupational health disorders, such as exposure to ground-up plant matter, organic fibers, bacterial, fungi soil, and pesticides. Silica is found naturally in the environment. It is a compound made from silicon and oxygen and can come in different forms. All silica forms are made from the same chemicals but can have different structures. Silica is divided into two main groups, crystalline silica and amorphous silica, non-crystalline silica. The most common type of crystalline silica is quartz. Other types also exist, but they are less common. In 1977, the U.S. Environmental Protection Agency, EPA, looked at the exposure risk of silica dust in cotton dust harvesting. Preliminary sample results indicate that cotton pickers were exposed to a free silica content mass of 7.9%, resulting in a hazard factor of 10.1 micrograms per cubic meter of air. Cotton strippers in baskets and trailers had, on average, 2.3% free silica exposure, but a much higher hazard factor of 23.3 micrograms per cubic meter of air. This evidence was the first published information that agricultural workers were exposed to respirable crystalline silica. The level of dustiness varied according to the type of work. Among 42 types of occupations, the highest amounts of dust were observed during thrashing, an indoor occupation, 57.5 mg/m3 on average, and during combined harvesting of grain, 35.7 mg/m3 on average. The highest exposure was observed in August, 23.4 mg/m3 in the group of tractor drivers, and 14.2 mg/m3 among private farmers. The calculated annual mean weighted values for the concentration of dust at the worksite of 10 examined tractor drivers remained within the values 5.3 to 10.8 mg/m3, whereas for 7 examined private farmers, it was within the values 3.6, 10.7 mg/m3. We know that crystalline silica is naturally found in soil and rocks, and when disturbed, it can become airborne as dust. This is common in agriculture during plowing, tilling, harvesting, or working in dry, dusty conditions. Operating grain harvesters, tractors, and other farming equipment can stir up dust containing crystalline silica, particularly in areas where the soil is rich in it. Crystalline silica may be found in feed or bedding materials used for livestock, especially in areas where grains like wheat, barley, and oats are grown, which are typically higher in silica content. This graph represents a longitudinal study using the OSHA sampling data between 1984 and 2013. It shows that many agricultural and forestry operations are exposed to crystalline silica dust above the ACGIH threshold limit value, TLV, and NIOSH recommended exposure limit, RL. soil can indeed contain crystalline silica, a naturally occurring mineral. Particles that are small enough to be inhaled deep into the lungs are called respirable. Breathing in respirable crystalline silica dust can lead to serious lung diseases, including silicosis, and increase the risk of lung cancer. To mitigate the risks, farmers and farm operators should implement measures to control dust exposure, such as using wet methods, providing adequate ventilation, and wearing appropriate personal protective equipment, PPE, like respirators. Training and education regarding the health hazard and a medical surveillance program would help with early diagnosis of pulmonary or kidney disease. Silica-bearing deposits are found in every landmass and strata from every period of geologic time. Quartz, from which most silica deposits are derived, is hard, inert, and practically insoluble. Quartz survives numerous weathering processes and, as a result, constitutes approximately 12% of the continental landmass. Alpha quartz is found in trace to major amounts in most rock types, e.g. igneous, sedimentary, metamorphic, argillaceous, sands, and soils. Quartz is a major component of soils, composing 90–95% of all sand and silt fractions in a soil. Crystalline tritomite and cristobalite are found in acid volcanic rocks. Cristobalite also occurs in some bentonite clays and has traces in diatomite. Although rarely found in nature, coesite and stishovite have been found in rocks that equilibrated in short-lived high-pressure environments, e.g. meteoritic impact craters. And kedite has been found in high-altitude atmospheric dusts, which are believed to originate from volcanic sources. IARC 1997. The OSHA sampling database indicates on a small sample set of agricultural and forestry workers who were exposed to respirable crystalline silica. Of these 22 air samples collected by the OSHA compliance officers, the amount of crystalline silica was 9.5%. Crystalline silica in the bulk soil samples were about 32.9%. Agriculture and farming work activities with a greater likelihood of exposure to crystalline silica include nearby road construction that involves drilling and blasting, hauling logs or driving tractors in very dusty conditions, hauling gravel, road dust, or the material being transported, working on a landing or at a dryland sort or tilling topsoil that contains silica, sandblasting, loader operators at sawmills transporting logs that were dried outdoors in sandy loom areas or mill yard, using fly ash from local pulp and paper mills for land use. In March 2016, OSHA issued a final rule called Occupational Exposure to Respirable Crystalline Silica, 29 CFR Parts 1910 General Industry, 1915 Maritime Industry, and 1926 Construction Industry. The rule became effective June 23, 2016. In the fall of 2022, the Mine Safety and Health Administration, MSHA, developed protections for miners exposed to RCS. OSHA did not promulgate a standard for the agricultural industry, 29 CFR Part 1928, since it was believed that exposures were short-term and there are no occupational health standards for the industry. Well, can OSHA cite the General Duty Clause? This means that employers must protect employees from any serious hazard once they're aware of it, whether OSHA's rules specifically address it or not. To cite Section 501, OSHA must prove that the employer failed to keep the workplace free of a hazard to which its employees were exposed. The cited hazard was recognized. The hazard was causing or likely to cause death or serious physical harm. A feasible and practical method to correct the risk was available. Prior to 2016, the OSHA permissible exposure limits, PELs, for respirable crystalline silica were much less protective and varied somewhat by industry, general industry, shipyards, construction. For example, in construction, shipyards, etc., older OSHA PELs effectively allowed up to 250 microg/M3 in many tasks. In general industry, older OSHA PELs, depending on silica content, etc., were around 100 microg/M3 for many operations. The new OSHA PEL for respirable crystalline silica was set at 50 micrograms per cubic meter of air, 50 microg/m3, averaged over an 8-hour time-weighted average, TWA. The rule also introduced an action level at 25 microg/m3, 8-hour TWA. When exposure is at or above this level, certain additional requirements, e.g. exposure assessment, monitoring, medical surveillance, etc., are triggered. However, tasks such as handling siliceous soil, sandblasting of equipment, grain handling in dusty conditions, concrete work, or mixing feed ingredients that include silica-containing additives could create relevant exposure. Agricultural tasks are often outdoors, which helps with dispersion, but certain conditions, dry soil, high wind, enclosed barns, or storage areas, may concentrate silica dust. Employers in agriculture should evaluate whether any work tasks exceed the action level, 25 microg/m3, and if so, apply the control and monitoring requirements. The current OSHA, Standards for Construction, Maritime and General Industry requires exposure risk assessment of the work tasks using air monitoring and surveillance. Action level of 25 micrograms per cubic meter of air over an 8-hour time, weighted average exposure, TWA. Maximum permissible exposure limit, PEL, of 50 micrograms per cubic meter of air over an 8-hour TWA. Respirators above the PEL. Written exposure control plan. Housekeeping requirements. Medical surveillance including chest X-ray, pulmonary function, and tuberculosis tests. Hazard communication of the hazards and controls with laborers and other staff members, and maintaining employee air monitoring and medical surveillance records for the duration of employment, plus 30 years. This picture represents the amount of crystalline silica workers are exposed at the current OSHA PEL without the use of respiratory protection or other controls. If we continue to double the airborne concentration, then we need to reduce the time of exposure. In this case, the time of exposure to 100 micrograms per cubic meter of air would be reduced to a maximum of 4 hours. If the airborne exposure continues to double to 200 micrograms per cubic meter of air, the time of exposure would again be reduced in half to a maximum of 2 hours. The same would apply to higher levels of exposure. On the other hand, the OSHA PEL should be lowered if farmers and agricultural work extended work hours. As an example, working a 16-hour work shift would technically lower the OSHA PEL to 0.25 micrograms per cubic meter of air. Currently, OSHA does not have a provision to allow a reduction of the occupational exposure limit for extended work. Physical properties of soil include color, texture, structure, density, consistence, temperature, and porosity, which is the fraction of pore space in a soil. In turn, these properties affect air and water movement in the soil, and thus the soil's ability to function. Colors of soils vary widely and indicate such important properties as organic matter, water, and redox conditions. Aggregates play a major role in determining a soil's friability. A soil is friable when moist soil crumbles into aggregates when crushed with only light pressure. There are 4 different types of soil: clay, loam, sand, and silt. Soil used in construction or landscaping on farms may include crushed rock, sand, or stone dust, all possible sources of RCS. Clay soil is defined as soil that is composed of mostly clay particles. Soil that consists of over 50% clay particles is referred to as heavy clay. It is prevalent in many parts of the world. Loam is considered to be the most desirable medium for growing vegetable crops, flowers, shrubs, trees, and many other types of ornamental plants. Loam is soil composed of sand, silt, and clay in relatively even concentration, about 40-20% concentration respectively. Sandy soil in which sand predominates is classified, logically enough, as a sand-textured soil or simply a sandy soil. Sandy soils are coarse in texture. Not all sand is made solely of silica, although it's a common component. While silica in the form of quartz is a major constituent in many types of sand, especially those found in inland continental and non-tropical coastal areas, Other minerals like calcium carbonate and calcium sulfate also contribute to sand's composition. Silt soil is finer than sand, but still feels gritty. Silt is commonly found in floodplains and is the soil component that makes mud. Soils with a lot of silt make excellent farmland, but erode easily. This is the soil blown away in dust storms and carried downstream in floods. Silt soil is similar to loam soil, but contains smaller ratios of both sand and clay particles. It feels smooth and silky, while retaining water well, but may drain slowly depending on the exact clay-silt-sand ratio. Because of this, gardeners usually amend silt soil, mixing in mulches, fertilizers, drainage assistance particles, such as sand or other soil additives to solve drainage issues and provide the proper growth medium for most plants. Peat and other organic soils are formed by decay of plant material and should not have any silica in them. However, since silica is a component of dust, and dust accumulates when these soils form, there will be some amount of silica. The amount can vary from a few percent to as little as 0.1%, but it will be there. Sandy soils contain the highest amount of RCS, often 70–90%. It is common in arid regions, riverbeds, or coastal areas. There is a high risk during tilling, excavation, and earth moving. Loamy soils contain a mix of sand, silt, and clay. Silica content depends on the proportion of sand and mineral composition. Still a risk, especially when dry and dusty. Gravelly or alluvial soils are formed from weathered rock and river deposits. They often contain fine, quartz particles, and disturbance can release airborne silica. Volcanic or ash-rich soils may contain cristobalite or tritomite, which are more toxic forms than quartz silica. These types of soil can be found near volcanic regions, such as parts of California, Hawaii, Italy, Indonesia. Construction fill or imported soil used in landscaping may include crushed rock, sand, or stone dust, all possible sources of RCS. This map illustrates the global threat of RCS for various types of soils. Many seasonal workers are exposed, often unknowingly, in agriculture and farming. Silica exposure causes irreversible disease and contributes to significant mortality and morbidity. In many places, the health protections aren't sufficient or well enforced. Silica plays a critical role in soil chemistry, influencing several soil properties and processes. One of its primary functions is as a nutrient source for plants. Although not considered an essential element for most plant species, silica has been shown to enhance plant growth, improve resistance to biotic and abiotic stresses, and promote nutrient uptake efficiency. Silica in the soil undergoes weathering and dissolution, releasing soluble forms of silicon that can be taken up by plants, contributing to their overall health and resilience. It also affects soil classification and provides valuable information for soil mapping and land management. There are few studies of agricultural dust exposure, although recent research has begun to fill some of the gaps in this area. Most studies are on non-randomly selected populations, and thus a population-based picture of inorganic dust exposure is lacking. Characterization of dusts has been limited generally to total and respirable fractions, and speciation has primarily been total inorganic fraction and respirable quartz. These images represent ultrafine, submicron, respirable, and coarse particles, all less than 10 microns in size. Silica is extracted from agricultural waste by various methods like thermal treatment, acid leaching, alkali-based, biologically, etc. Agricultural waste is a cheaper, safe, and environmentally friendly source for silica production. This presentation cites several sources of potential silica exposure derived from agricultural waste, such as rice husk, rice straw, corn cobs, and sugarcane bagasse. X-ray spectrum analysis of crystalline silica in sugarcane bagasse, corn stalks, and rice hulls are shown here. The formation of crystalline silica was confirmed in sugarcane bagasse and corn stalks, with higher intensity in the sugarcane, while the rice hull silica is represented by an amorphous structure. It should be noted that corn stalk silica shows a crystalline spectra of lower intensity, since corn stalk residues contain a mixture of both amorphous and crystalline silica that are inherited from biomass characteristic. This study assessed respirable silica exposure of farm workers in eastern North Carolina. Sandy soils in this region have been shown to contain high levels of respirable silica. Personal breathing zone samples, N equals 37, were collected from 27 workers at 7 farms during various agricultural activities. Respirable silica exposure was observed to be associated with agricultural activity, soil moisture, relative humidity, and wind speed. Most of the variation in exposure, nearly 79%, was explained by agricultural activity and soil moisture. The observed percentage of silica levels, mean 34.7%, were almost twice as high as was reported in other studies of California agriculture. This may be due to the loamy sand and sandy loam soil types in the regions in this study. In agriculture, respirable silica exposure is highly variable, but the potential for exposures above the threshold limit value of 0.05 mg/m3 exists during particular agricultural activities such as field preparation, planting, hand and mechanical harvesting of soybeans, cotton, sweet potatoes, and tobacco. RCS exposures in this study varied considerably between various work activities, ranging from the limit of detection for cotton planting to 3.9 mg/m3 for sweet potato planting. The mean respirable dust and respirable silica concentrations for workers on uncabbed tractors were at least an order of magnitude higher than for the other 2 job functions. Significant differences were observed between uncabbed and cabbed tractor drivers, riders, and workers on foot. Farm, agricultural activity, and relative humidity were the most significant determinants of RCS exposure in the regression analyses. The significance of the other predictor variables, job function, soil moisture, air temperature, relative humidity, and wind speed, was investigated by adding each variable into the base model separately. This slide represents the airborne dust exposure from harvesting downed corn on a farm in Grinnell, Iowa, in late September. Particulate matters of diameters less or equal to 2.5 microns and less or equal to 10 microns, and the total suspended particles were sampled in real time during peanut harvesting in Henan Province, China. The airborne particle concentrations and particle size distributions were measured. The dust particles discharged during the mechanized peanut harvesting were concentrated within the 2-30 micron size range. When the wind speed was reduced below the settling velocity of the largest particles, the more massive particles were carried downwind. The amount of free silica in the dust samples was determined by X-ray diffraction analysis. Both the total dust and free silica concentrations exceeded the occupational exposure and threshold limits. RCS does not normally present a major threat to health because it is bound up in materials and not present in the air. We breathe. But modern work practices disturb this and release RCS into the air, where it can enter the lung. This can present a serious occupational hazard. The reason RCS is so dangerous is due to the nature and fine shape of the small particles involved. Exposure to RCS can be dangerous whether it is a long-term exposure or a brief acute exposure. Exposure for even a few months has been shown to cause serious problems if the levels present are high enough. It is not safe to assume that one is only at risk if working in a field where there is potential for RCS exposure over decades. Elevated occupational exposure can lead to lung cancer, as RCS is a known carcinogen, as well as silicosis in one of 3 forms: classic silicosis, accelerated silicosis, or acute silicosis. Classic or chronic silicosis, the most common type, can occur after decades of low-level exposure in work settings and only becomes apparent when progressive lung decline becomes noticeable. To date, Exposures to RCS at levels that produce adverse health effects have only been reported in workers who have been exposed by inhalation for a prolonged period of time in silica industries. Health effects associated with occupational exposure to RCS are silicosis, a progressive, fibrotic lung disease, chronic obstructive pulmonary disease, COPD, lung cancer, renal toxicity, increased risk of tuberculosis, and autoimmune diseases. Of these, silicosis and lung cancer pose the greatest concern to human health. Other health effects from RCS exposure include shortness of breath, chronic phlegm or cough, reduced lung function, emphysema, chronic bronchitis, and interstitial fibrosis. This case study represents a 67-year-old male patient with an abnormal CT scan. He was found to have numerable upper lobe predominant centrilobular nodules. He had initially presented to his primary care provider with a complaint of dyspnea. He was a former smoker with an 88-pack-year history. He had recently moved to the U.S. from Mexico. His physical exam was unremarkable. He was subsequently ruled out for TB, with 3 negative sputum AFB smears. Given the lack of relevant exposure history, a bronchoscopy was done. Transbronchial biopsy samples were significant for birefringent silicate particles and anthracotic pigment consistent with pneumoconiosis. The patient worked as a pepper plant farmer in Mexico for over 30 years. Of note, the pepper plants were grown in sandy soil. Silica exists in amorphous and crystalline forms that have unique physiochemical properties. Amorphic silica is found in biological matter such as plants, sponges, algae, fungi, and bacteria, and non-vegetative matter such as volcanic glass, colloidal sols, and powders. Amorphic silica is not considered toxic. In contrast to the random orientation of molecules in amorphous silica, crystalline silica exhibits a fixed, repeating, polymerized silicon-oxygen tetrahedral framework. Crystalline silica exists in various forms, including alpha quartz, beta quartz, alpha tridymite, beta tridymite, alpha cristobalite, beta cristobalite, keatite, coesite, stishovite, and mogonite. Alpha quartz is the most common crystalline silica and the most biologically toxic form. Agricultural workers in the United Kingdom inhale high concentrations of mineral dust that threaten their respiratory health. These mineral dusts are primarily composed of crystalline silica and silicates. In these environments, routine work activities like plowing, tilling, and soil turning can release high concentrations of respirable dust. Measurements frequently record levels of 15 mg/m3 of respirable dust and greater than 20 mg/m3 total dust. These exposures place farmers at increased risk of lung damage from these significantly high exposure levels over time. Occupational exposure to RCS dust can occur from dry farming, dryland farming, and rainfed farming. Dry farming. It is production of crops without irrigation in areas where annual rainfall is less than 750 mm. Crop failures are more frequent under dry farming condition, owing to prolonged dry spells during crop period. The growing season is less than 200 days. It is generally practiced in arid regions of the country. Dryland farming. Cultivation of crops in areas receiving rainfall above 750 is known as dryland farming. Dry spell during crop duration occurs, but crop failures are less frequent. Semi-arid regions are included under this category. Dryland areas also contribute significantly to wheat, cotton, and rice production. Rainfed farming. It is practice of crop cultivation without irrigation in areas receiving 1150 rainfall, mostly in subhumid and humid areas. Here, chances of crop failure and water stress are very less. Respirable quartz measurements from a South African wine farm ranged from not detectable to 626 micrograms per cubic meter of air during harvest, and confirmed the quartz risk, as some concentrations exceeded accepted occupational exposure limits in all jobs evaluated. Even though the majority of respirable dust concentrations were well below a commonly used occupational exposure limit of 2 micrograms per cubic meter of air. In South Africa, SA, very little is known about silica exposure in the farming and agricultural industry. The objectives of this reported study were to measure inhalable and respirable dust and its quartz content on 2 typical sandy soil farms in the Free State Province of South Africa for all major tasks done on the farms, and B, to characterize the mineralogy soil type of these farms. The potential health effects faced by these farm workers from exposure to RCS are of concern. The investigation was conducted at the Agriculture Research Station of the College of Agriculture and Natural Resources, University of Tehran, Karaj, Iran in July of 2018. The agricultural farm was characterized by a semi-arid climate with a mean air temperature and rainfall of 13.7 degrees C and 245.5, respectively. 2 field sites with 2 management practices conventional tillage and no-tillage systems were selected for this study. Both fields were cultivated with wheat and corn rotation for 15 years before the experiment. During these years, in the conventional tillage system, post-harvest crop residue was removed from the farm for food and bedding of animals, building materials and household fuel, but in the no-tillage system, crop residues remained on the farm. Pepper farmers in China, Trinidad, and Pakistan may also develop silicosis due to exposure to crystalline silica in the soil of farmland when it's worked, such as plowing or disking. Both plowing and disking may release dust particles into the air that may include silica dust that can be breathed in by the farmer. This slide represents the amount of dust that can be liberated into the air during disking. Machine operators with closed ventilated cabs have a reduced occupational health exposure to RCS dust. Characterization of inorganic dust has been limited to total and respirable fractions of quartz silica. The highest dust exposures occur during soil preparation activities, such as tractors pulling equipment during plowing, dicing, and planning. These operations generate large dust clouds. Median total particulate exposures in an open cab range from 2 to 20 milligrams per cubic meter of air, but some exposures can exceed 100 milligrams per cubic meter of air. The respirable fraction in tractor cabs can be 40% of the total dust exposure. Total respirable dust concentrations can range from 1 and 5 milligrams per cubic meter of air. A study of rice farming in California reported occupational respirable dust concentrations at 0.52, 2.16 milligrams per cubic meter of air outside the harvester, and 1.77 to 5.24 milligrams per cubic meter of air outside of the tractor during field preparation. The dust generated by sweeper harvest activities includes significant PM10 emissions and some PM25 emissions in the San Joaquin Valley of California. Almond harvest creates a lot of dust, including significant PM10 emissions. Dust can be managed by using several engineering and administrative control strategies. Several studies have shown an increase in chronic obstructive lung disease among agricultural workers, although the specific causal agent or agents are often unknown. A study of grain workers in Vancouver, Canada found an increased production of phlegm and dyspnea associated with the workplace exposures and higher rates of airflow obstruction among retired workers. Increased respiratory mortality from RCS exposure is associated with a greater degree of collagenous fibrosis. 5 vineyard workers died of respiratory failure and pathological exam revealed interstitial fibrosis, chronic inflammation, and foreign body granulomas. Dust from loading and unloading grain from siliceous crops was evaluated. The identification and degree of exposure to respirable dust, crystalline silica, and endotoxins throughout the potato harvesting process was characterized harvest in the San Luis Valley of southern Colorado. The agricultural practices specific to potato harvest, the geographic region, and the soil of San Luis Valley are believed to contribute to occupational risk. All exposures were based on 8-hour time-weighted averages. Exposure impact included location of the farm, soil type, such as sand, rock, or loam, job description, weather conditions, wind, rain, wet or dry soil during harvest, humidity, and temperature. Results of air monitoring include 122 samples collected. 93 revealed the presence of respirable dust, and 18 detected respirable silica, quartz. The maximum respirable dust exposure was 5.05 milligrams per cubic meter of air. Respirable silica was 0.105 milligrams per cubic meter of air, and the percent silica was 12.85%. A trash separation apparatus from a harvester uses rotating knives to chop the sugarcane stalks in the field. The airborne exposure to the equipment operator has yet to be studied for RCS exposure. In this study, Australian wheatbelt farmers were noted to commonly work extended hours and shifts during harvest due to rigid timing deadlines. Results showed that 40% of farmers were exposed to concentrations of inhalable particles greater than Safe Work Australia's workplace exposure standards for grain dusts, assuming a 16-hour working day over 5 shifts. 22% were exposed to concentrations that were above the adjusted standard for 12-hour shift. Dust exposures measured during harvesting operations could be considered as predominantly exposures to grain dusts, and therefore the measured concentrations have been compared with the Safe Work Australia (SWA) workplace exposure standard for grain dust oats, wheat and barley of 4 mg/m3 from farming activities, including grain dusts, have consistently been associated with adverse respiratory health effects, including chronic cough, chronic phlegm, reduced lung function, shortness of breath, and wheezing. Forestry mulchers are mainly used to clean up and maintain forests and green spaces in general, removing branches, shrubs, and bushes and pruning trees. People also use them to prepare soil for planting seeds and trees, making trails, cleaning out burnt areas, and creating fire breaks. The airborne exposure to the equipment operator has yet to be studied for RCS exposure. Not all respirable crystalline silica dust exposures come from farm and agricultural operations. In this scenario, a farmer walks in dust storm on drought-stricken land near Felt, Oklahoma in August 2013. Only a few studies clarified a relationship between dust storms and exposure to RCS. This is another example of a brief exposure to RCS from a dust devil. When they occur in nature, the dust exposure can be brief but intense on a farm. Grain contains a large amount of mixed dust, including grain husks, bacteria, pests, microorganisms, and mixed fine sand, which contains both crystalline and amorphous silica. The amount of silicon dioxide during grain loading and unloading can range from 18.8% to 22.3%. Hence, agricultural and farm workers may be exposed to RCS during grain harvesting. Dust generated during grain handling can pose a health hazard and is an air pollutant. This study was conducted to characterize the particle size distribution of dust generated during handling of wheat and shelled corn in the research elevator of the USDA Grain Marketing and Production Research Center, and determine the effects of grain lot, repeated transfer, and grain types. The percentages of particulate matter, PM-2, 5, PM4, and PM10 were 5.19%, 9.81%, and 34.1% of the total wheat dust, respectively. For shelled corn, the size distributions of the dust samples showed similar trends among transfers, but differed between the upper and lower ducts. The percentages of PM25, PM4, and PM10 were 7.45%, 9.98%, and 28.8% of the total shelled corn dust, respectively. Overall, the corn and wheat differed significantly in the size distribution and the rate of total dust generated. While many of the RCS health effects can be prevented or minimized by applying appropriate control measures, as noted by the recent work by Kramer and colleagues, along with Schenker et al., they found that agricultural farm workers showed significant knowledge gaps regarding the identification of farming hazards, including exposures to harmful dusts and chemicals, use of protective equipment, and use of other control measures to reduce exposure. OSHA has created health standards for exposure to RCS in general industry and the construction trades. MSHA has created RCS health standards for miners. OSHA rules do not apply to agricultural workers since it is believed that those workers are only exposed to seasonal periods, and there is a limited information on the frequency and duration of occupational exposure. As demonstrated in this presentation and OSHA sampling data, agricultural workers and farmers can be exposed to elevated levels of RCS. More information regarding occupational exposure and controls of RCS can be found in the published OSHA literature.